Okay, so the only thing that before we start, what I wanted to do is to discuss like a couple of things. So the first things to be discussed is actually that this day, so Thursday will not be E4, but will be E3. But I mean, it is not a big deal. Like we'll just remind you, we can go together.
It is there?
No, E3 is the one there. It's basically like when you enter, like there is the corridor, and before going down, like the last room is the E3. Yeah, should be that one. No, wait, this is the E0. No, the E3 is actually the one close to the secretary room, but we will go together, so no problem about that. And then I have a question to the four of you, because the point is the following, like so far, you see that we have this packed schedule. So basically like on Thursday, Friday, relax, Monday, Tuesday, Wednesday, Thursday, Monday. So like we are a bit in a rush for a lot of reasons. And I realized yesterday when I was thinking about that, that even though like in the group, we always did just the answer, I think actually in the answer, you don't find what you will really need for like making all the exercise in your life as a PhD. Because as you may have seen already, and let's see if that goes, already yesterday, then like at one point I give you one tip, and the tip was like to do some scripting. That was this one. So
Yes,
the for loop. Yeah, the for loop.
Yeah.
Okay, this
Yeah,
one.
the tip.
So this is the key. So this is basically you will need to be able to during your PhD to do some bash programming, and as well in my case also some Python program. And we are not covering that here. There is no time to cover it here. But I was wondering myself whether it makes sense. I mean, if you are, let's say, challenged enough to try to do that, to make a break, like in the middle of the first two lessons, also not to get saturated with DFT. So to stop this Thursday. Then between Friday and Wednesday, we do two different projects between the four of you. So two of you can try to do some Python scripting. Santiago, I think you already did.
Yes.
Okay, so you can be in one of the two groups. And the other two can try to do some bash scripting. And why I was thinking yesterday about that? Because the point is that you will need to do this script anyway at one point of your PhD. And in my case, what happened is that, let's say, in the moment where I was more free, that was basically like the first 2-3 weeks, I was a bit bored because I don't have much to do. And then like in the following months, I had to do everything. So I needed to do all the scripting in a rush, and that was a bit painful. So perhaps it will be like more interesting for all you to make this in the middle. So let's say between Friday and Wednesday, 15. We don't have any class. I mean, I will give you like information by slides. And then you divide into groups where two of you develop some script that you will need in the future anyway, no matter why, and then you will have them and you don't need to work on that later. And the other two of you, others two script with Python, okay?
Yes, for me.
Are you okay?
So the second part of that course would be passed through the...
Exactly. So we postpone and we start again from Thursday 16. So what will happen is simply that instead of finishing on Monday 20, we finish on Thursday 20.
But that day it's Thursday 23. It's a free day because it's Santa Tecla.
Ah, no, 24. Sorry, wait, let me check.
Yes.
Yeah, we have the
but then Friday 24.
Yeah. Okay, but then I need the calculation, bro. Because that will be, so we will need to recover like 1, 2, 3 lessons, and that means like, yeah, 1, 2, 3. Okay, yeah, we may do then we will do it on the 24th then. I mean, it's not such a big deal. Yeah, because the 23 is holiday. Okay?
Okay, I understand.
Would it be good? It's not a problem if we postpone by 3 days?
No, perfect.
Problem.
Okay.
What should we do?
I mean, the only thing that will change is that these lectures are cancelled.
Okay.
And we basically move them from Thursday 16. And what you do here, like then I will send you like proper slide tomorrow, like this is, I will organize and tomorrow I will show you everything. Today, I just wanted to know if it makes sense to organize that or not. So what will happen is just that between this Friday 10 and Wednesday 15, we will not have frontal lectures, but all the four of you will have two different projects about scripting that you need to do anyway. Okay? So you will not do DFT, you will not do VASP, but you will prepare some command that you will need later for your projects. Okay? Clear? More or less. And just to give you an idea about what the projects will be. So you will be divided into groups. And I was thinking that since Marian doesn't have the virtual machine yet, and I don't know when she will have it, she can also work on Python, because Anaconda works also on Windows. And then Santiago, since you already work with that, you can also work on Python, because that will be probably the most challenging part, but probably also the most important. So tomorrow I will tell you everything much better, but the idea would be that you two will have to work together in preparing two scripts. One of the scripts should be able to prepare crystalline facets out of bulk. So basically, like Anson tree of VASP will be all about surfaces, but in this case, you will need to be able to have a script that from the bulk structure that you have, generate all the facets you need. Because usually that is something that you do with a Material Studio on Windows. It takes a lot of time. It's very, very open to error, so it's better to do it automatically with Python. And then another mob script to calculate the surface energy, but these I will provide the details tomorrow. Instead, for Siken and Enric, 3 scripts with Bash. That is much easier. So Bash is exactly all this 4 stuff that you already have seen, but it's just that here you will need to have 3, and all of them will be about automatically generating the input for the calculation. So you have seen in this Anson that all the input were done. The problem is that that will not be like that during your study. So during your study, you will need to generate all the input, and you cannot do it manually. So you will, like, one of the script will be rather easy. So it will be just to generate directly the key points file from your postcard, because as we say yesterday, and then later we'll discuss better about this key point file. It's depending on the structure you have. So there must be an automatic way to get the structure from the postcard and already generate the key points that you need without needing to do it manually. And then the other 2, one will be again rather easy, and I will explain tomorrow why it's needed, but will be about ordering surface layer. So make sure that some of them are fixed, some of them are free. And the third one about adding molecules there. But again, tomorrow I give you all the details. That was just organized. So since the 4 of you say that it's okay, then tomorrow I give you the proper organization, and then we discuss better. Then the other things that I already want to discuss now, and I think I can go directly to.
Sorry, Federico, you said that for me and Marian that we would work on Python. We have to do 2 scripts, but you just mentioned one.
No, the second one will be about the surface energies. So calculating automatically the surface energy.
Okay, sorry.
No, don't worry. I mean, I said it very fast because I didn't want you all to focus on that. So then I wanted to say a general things about the answer, okay? Because I think that you had not a general problem, but you had a general question. I think Siken and Enric. So we can solve it now. In the sense that one of the things that you have seen, and maybe I can open a terminal, is, and I can also kind of make it larger because otherwise here we don't see anything. Okay, so okay, now I will just connect to, well, I can directly do it through Tekla actually. So now I'm entering, okay, I use the reduce. Okay, yeah, I had the password, the capital one on. Okay, no, so probably you have already seen yesterday that something strange, and Siken comes to ask me, and now I have the answer of what we were talking yesterday. So if you see here the key point file, maybe I can still put it a bit larger so we will see better. Okay, here you see, like, okay, gamma point only, you have 1 key point, reciprocal because it's in unit of reciprocal lattice vector, 0, 0, 1, the 3 coordinates, and then you have weight. And we could not understand properly what the weight is. And now we check what the weight is. So you need to think that what VASP directly does is not taking all the key points that you give you. It still tries to optimize the key point mesh. So VASP tries to take all the key point mesh and say, look, can I reduce some of them? Maybe some of them are just the symmetrical of the others. So maybe I don't need to calculate both of them. So let's make it like a bit more clearer. So you need to think as in, okay, so like that. And I think here you should see it. Okay, so you need to think that, let's say this is a line, okay? Let's work just in one dimension. And you decide to have 3 key points. So you decide to have one in this position, one is this position, and one in this position. And let's assume that this one is the center of symmetry of your problem, okay? So basically, this key point and this key point are symmetric. Then what VASP does, since it doesn't want to lose time, and since we work with periodic boundary condition, it just focuses on this part. So basically say, okay, this one is not needed because the system is symmetric. So, I mean, you need to think about something similar, right? Symmetric. So it means that this thing is equal to this one. So there is no need to calculate both of them. You just focus on this part. And here it comes the weight, because then in order to calculate the overall energy, what you do is you sum, let's say that you calculate like you have a contribution from our key point. Okay, so E1, E2, and E3. So what, it's really hard to write with as well. So what VASP does then is not to take anymore like all the 3 key points, as I said, but it just focuses on this part. So it calculates like the energy, or it gets some properties by their sum. But what is the problem is that if we don't put the weight, then VASP will account this point or this contribution as 1 and this contribution as 1. But that will be wrong, because in your system here, this one are 2 points, while this one is just 1. So what you should do instead is that this thing should be 1/3 and this thing should be 2/3. Because even though like VASP is not considering both of them, still in the system both of them exist. It's just that VASP avoid one of them because the same result that you get for E1 will be equal to E3. Okay, so that's the reason why you need to put the weight. In this case, the weight is useless because you have 1 key point. So of course, if you have a single key point, the weight are the same. But if, for instance, you added another line here and you had 2 different key points, so let's say this 3, 1, so 1, 2, 3. Then in that case, you needed to put the weight, because otherwise maybe VASP would have said, okay, these E1 and E2 are the same, so I just don't consider that. But then it would say, okay, then the contribution of these key points and this key point are the same, but they are not, because this one is symmetric with this one. So here there are two key points and just 1. So the contribution of this one will be higher than this one, okay? Is it a bit clearer now?
Yes, but in a case that there is no symmetry, and for example, there are 3 points, and we are computing the coordinates of the 3 points, we must put 1, 1, 1, 1, 1, or 1 divided by 3, 1 divided by 3.
I mean, in general, like, I think it doesn't matter, because
it's like a reading proportion.
Yeah, I was reading and studying. What is important is the proportion between the two. So like then VASP internally scale it up. So if you put like 1, 1, 1, then it's like 1/3, 1/3, 1/3. Okay. If you put 2, 2, 2, 1/3, 1/3, 1/3. The only important thing is that you put 1, 2, 4, then you scale it accordingly. So 1 will account for 1/4, 1 half. Okay.
I don't understand what that 1 means.
That
1 means we have what? We have energy.
I mean E1, yeah. So this,
no, I mean the one.
The one here. No, this is the weight. So this is how much VASP give, like, let's say how much weight VASP give to this energy, this energy, this energy. Okay, I'll try to make another example that is a bit more general.
And 1/3, 1/3 means
1/3.
Weight.
Yeah, it's just that this one, that this one is normalized and the sum is 1. So, or if you can put like 33%, 66%. Okay. So the point is that just here you have 3 points, okay, and this one, like this one is reduced by VASP, so this one is not there anymore. But the point is that you cannot just say, okay, the weight of this point and the weight of this point is the same, because the problem is that this point should be counted twice, because there was also the Z1 that was reduced. So the weight of these things should be 2 times this one. So you cannot just put 1 and 1. You cannot say that the weight of these two are the same, because otherwise, like, you will lose some information, the information of this one. Okay? So it's a bit like you need to think like when you do any statistical analysis, you put weight to some parameters. There are some parameters that are stronger and some parameters that are weaker. But if you always put 1 to every parameter, then you lose some information. And that is the case where you put the weight. But if I were you, I would not like spend too much time on this weight, because usually it's calculated automatically by VASP. It's not something that you will need to do yourself. You will not define yourself the key point mesh. There are some packages that we will see tomorrow that already generate the mesh for you. So it's good to know that, because it's good, but don't worry.
Okay, I mean this one that we put here in key point 001, and this one means you have put from the bound. I mean,
this one that you see here just means that you have just a single key point.
Yeah.
So the single key point has 100% weight on the final estimation of the energy, because you just have one.
I mean, you have this one means what have you put in the bound?
Yeah, it's the same.
One and one.
Yeah.
One.
Yeah. Okay.
Does it not make sense? I mean, this means nothing. Because we need to do it by 30 and
yeah, but the point is that this case is a case where you have 3 key points, and in this case you just have 1 key point. Okay, and this number, as I say, this number are wrong. So this number is what, like, if you put it, then it's a mistake, because here you have 3 key points and you're just considering.
Yeah, it wouldn't consider the symmetry.
Exactly. Then you will lose the symmetric part. Okay.
Oh, we just need to put a 1 in the center. And this one.
In this case, yes, but because in this case E1 and E3 don't exist, because you just have one single point in the middle. Okay. Good. So I think that with that, like, this was what I wanted to tell you at the beginning. So we can start with potential questions. So who want to start?
We have almost the same
Okay, then go ahead. Then for you, 30 minutes together. Go.
Okay. No, I thought.
I mean, I think will be much faster. But go ahead.
No, yes, but I have also my own little questions. So if you want to start, and I don't know now which are the other questions that we have in common.
Vamos a responder primero las energías libres o ya empezamos con la energía
libres.
Bueno.
Ask yourself.
Okay.
I don't remember now what are you referring.
Just give me. So in which one is it?
Yes.
Here we have the problem because
the system is 1, 1, 0. Yeah, like remember always to tell me the system, because otherwise Mario cannot see. So
okay.
This is the system.
I mean, when we want to look for the energy, and I remember yesterday when you taught me how to do this, and I know that they're just to put the brief energy W of car, but I remember that yesterday they were just two values.
Yeah.
But today when we look for it, we have found this for.
Okay, yeah. So you are in the case 1, 1, 0. Okay.
I think all of them will have the same problem.
Yeah. So okay, but this is not a problem. So you're already entering the solution. Okay. So if I do that myself, I should find just 1. Okay.
What?
Yeah, I just find 1. Okay. But why I just find 1? Let me enter Tekla, because then it's easier, because then I can access also your own calculation. So now I can go to home, okay, 1 and then 1, 1, okay. Okay, so now if you do like this, okay, let's check before the obstacle what you have. Okay, the obstacle you just have 2.
Yeah.
Good. And then if you do graph,
I didn't change any class.
yeah, there is a problem. Okay, this is okay, I understand now. Okay, so now I tell you. So the difference is the space. Okay.
Where are the space? Sorry?
You see, like here there are 2 spaces. Here there is just 1 space. So here 2 space. Here 1 space.
With just 1 space, there are 2 results.
2 results, and with 2 space there is 1. And now I tell you why. So we would have discussed that yesterday, but it's already good to go through this. So if you open the OTSI card, what you see is these things, okay? So you see DAV, DAV, and then one F. These DAV1, these are the ionic steps, the electronic steps. What does it mean, the electronic steps? That these are the steps where you optimize the electronic structures of your system. And the energy that you see here is the energy for each electronic step. So you see that you have two electronic steps, two energy, with just one space, because you see that there is just one space here. Okay? This energy here, with two space, is instead the energy related to the ionic step. That is the final energy you have.
Okay.
Okay? And what is the difference between the two? Again, we go through them tomorrow. But what VASP does, as we said yesterday, like he optimizes every time the electronic density, right? He starts with initial gas, then he moves to the second one, then he moves to the third one, and so on. So these things are the steps of the electronics, or the electronic density optimization. So what VASP does, let's see what you have in the INCAR. Well, in the INCAR you don't have anything, so you don't have.
I wanted to ask if those steps we are fixing them on the INCAR, right?
No, in this case, no. I mean, you have to later, like normally you can do, but in this case we are not, because we are not giving any parameter.
Okay.
So the fact that you don't give any parameter means that what VASP will do will just to take the input, the default value, sorry, the default value that we don't set. So in this case, what VASP did, took the default value for EDF, that is basically like the threshold that you're setting. So the default means that whenever you get to the difference between like two ionic steps, that is within I think e to the power of -5 electron volt, then your system is electronically converged. Okay, and since your system is electronically converged, then you can move to defining the energy of the ionic step. Okay, that is this one. So what is important for you to remember is that this system for sure, it's a bad one because you don't have oxygen atoms alone, and that's why you don't have any parameter. But what will happen is just that VASP star take the electronic density that is assumed for this single oxygen, and then he said, okay, I try to optimize it. And since it optimizes, and you see that the difference between this value and this value is very, very, very low, because this is minus 0.31 electron volt, okay, because you see that is exponential to the power of 0, and you see that the difference is 1, 2, 3, 4, 5, is on the fifth line. And since the threshold that you put is -5, then he said, okay, this is electronically converged, so you can give the energy of the whole system. So this is the energy of the whole system. And just to let you show, like, these two values are the same.
Yes.
Because what happens is that you go to the second value of the electronic step, you say, oh, this is converged, and then this is the final energy of the system. So as I said yesterday, this is the important value, okay? Because this is the value of your system where it is electronically converged. While the previous two energy that you see here is simply because you are doing cycles to optimize the electronic density of your structures. Okay? Good. So, next one.
The presentation. The presentation will have the could we just go to
the presentation?
Yeah, please. And the energy. Energy, it's a free energy chips. This one will have the E, but I still and this with sigma tend to 0, and so we have the energy, but still we need to entropy and temperature.
Yeah.
So in the how could I have that?
Okay, so you will, I mean, about, I also summarize for you, Mariam. So the problem is that as you can say, what we are getting here, if we do the trick of before, we get the energy without entropy. And then what I was also telling you is that this energy for sigma that is equal to 0 is basically the energy without the entropy whenever you're assuming that you don't have slurry between the occupancy of the electrons. So basically for the, like, as
the absolute temperature 0.
Exactly, that the absolute temperature is 0. So whenever like you put the sigma is equal to 0, you're assuming that after the Fermi energy, your electrons occupancy goes directly to 0, so that you have something like that. Okay? But as I was saying, since this transition that is very, very, very abrupt is not easy to simulate numerically, then usually what you do with VASP is just to have a smearing, so to have a continuous function. So you have something like that. But since, as I said yesterday, the temperature that we are always applying with VASP is 0, then we need to come back to this transition and say what is happening is just that we take that we extrapolate this energy with sigma that tends to 0. Okay.
But sorry to interrupt, but in that graphic that you are drawing, the EX and the axis, which channel you need?
These are this will be the this will be the energetic state for your electron.
Yes,
and the y-axis will be the occupancy. Okay. So the occupancy means that it's either 1 or 0. That you can have either 1 electron or 0 electrons, and that's why this continuous transition is a bit unrealistic, because I mean, like, you cannot have half electrons.
Yeah.
So that's why, like, we need them to use this trick. And about including entropy, yeah, you're right, in the sense that here is just the energy that is closer to this enthalpy value, let's say, in the sense that is the closest to enthalpy, while entropy, in order to calculate this entropy, we need to add the standard things. So the, like the TS, okay, where S is the entropy that we need to calculate, and T is the temperature of your system. This you do with a correction that you apply later. So you calculate the entropy from vibrational frequencies. So you did some vibrational frequencies analysis, like for this VASP, for this answer. From that, applying another bash script that we have in the group, you can get the entropy, and then the temperature you just adapt according to the temperature of your experimental system. So if you are doing electrochemistry, it will be room temperature. If you are doing thermal catalysis, that plays much more role. But this value in heterogeneous catalysis is a correction that you apply later on this energy. So it's not something that is DFT related. Let's say you don't get the entropy from DFT. I mean, you get the entropy from the vibrational analysis that you calculate with DFT, but it's not something related to this energy. Okay, so we always get the energy, the electronic energy that is, let's say, very, very close to the enthalpy of your system. And then for that value, you apply later this correction for that. Okay, and later. Okay.
I mean, you mean in the calculation of the VASP in the energy, I mean the energy of the electrons could not change quickly like that.
Yeah, I mean, yeah, this exactly.
Could not change.
Yeah,
but they need to do this.
Yeah, and that is the smearing, and the reason why you have the sigma that is equal to 0. But that we will go through that tomorrow. So don't worry too much if you don't fully get it, because tomorrow we will see proper graph and it's easier to get. Okay, and just like
Sorry, another question related to this energy. So you say we can consider like the enthalpy without the 0 point correction.
Yeah, exactly.
But I don't know, when I think about enthalpy, I think about the sum of the internal energy mass, the product of the pressure for the volume. This contribution is considered taken into account, or is like an assumption that we consider that is negligible?
Exactly. Now, to my understanding, we don't assume it here. Exactly. So that is the problem. So apart from the 0 point correction,
this is a problem for all chemical engineers, because we always study like the big three energies, the sum of the enthalpy and the enthalpy contribution, and the enthalpy is the sum of the internal energy and all this stuff.
So exactly. So
I have always this doubt.
No, but this is correct what you say. So basically, this energy flows to the internal energy, and then the P per V, we are not assuming that this factor is so relevant under certain conditions. Okay. I mean, mostly because I think, yeah, like, I think you can correct it later again in case you want, like with the TS factor, like these things, okay? And just to show you what I mean for like all these things. So for instance, if you see one of my calculation for my own system, okay? So what you usually do, well, okay, now that I want to show something, of course I can find, let's go to something that, okay, that I have for sure. So for instance, here, well, there are a bunch of projects, and what I wanted to show is the one with zero, the coverage one. So here, for instance, I was calculating some transition state about like the CO-CO coupling. So these are basically just absorption energy. I mean, these are energy of different systems. And, okay, of course, it's not this one. I think, okay. Yeah, we can go to, let's see, probably was in that. No. Now, whenever you want to show something, you always take so much time to, okay, let's see this one. Yeah, probably this is one.
I see.
Exactly. So you see how many things we have, because if you do like sigma, so sigma in my case will be exactly a graph energy, I make just like a comment for doing that, but that will be the same. So if I do this, you see that we have like 5 of them, because here I have 5 ionic steps. So if you want to see the Otsikar will be like that, okay? So you see 5 ionic steps, different electronic steps. So in case you do the same as before, but you remove the space, then you see that we have much more, okay? Because now we are having all the things. Okay, now I need to stop and take to clear all the drawing. And then stop annotate. Excellent. So you see that we have much more now. And then what is important is that, so sigma is this internal energy, let's say, and then as I told you before, there is a script that you can apply, and what the script is telling you, and we can do like gives okay, B, okay, yeah. This is a script to calculate gives free energy of liquid, gives free energy of gas, internal energy, entropy multiplied by 10 to the power of 3. Okay, so usually what you do, you just calculate the energy and then you apply the script that is already done. These things that you see here is the temperature. So you see, for instance, that if you put like 900, then you see that the entropy stabilizes in your system much more. So here you can see the difference between thermal catalysis and electrocatalysis. I mean, in electrocatalysis, like entropy is not that important. In thermal catalysis, of course, is much more important.
But could you repeat the importance? Why? Where are we seeing the importance of temperature? I don't understand.
No, in the sense that you see, like, so this is the energy. This is the energy of your system, okay, including entropy.
Okay.
So you see that when you have 900 Kelvin, the energy is more negative.
Okay.
Okay. So that means that what does it mean usually if you are studying like absorption energy means that your molecule is more strongly bounded to the surface rather than if not. So whenever you're going more down in energy means that your system is more stable. Okay. So what I wanted to say here is that since this temperature is higher like that than this, then entropy, like in this case, since you have more entropy, stabilizing your system much more than in the previous case. Okay, because in DFT, like let's say to have a lot of entropy in your system is not bad in DFT. Like usually entropy is in a bad way, but like in this case, the effect of entropy is to stabilize your system in the sense that you are like lowering the gives free energy of your system. Because you see, this is minus 351, this is minus 350, and if you take the standard one, I mean, this was minus 351.19, but because also that, like there are a lot of parameters to consider. So like the point is that because here we are also including the 0 point energy in this very same calculation. So the 0 point energy are the stabilizing while the other one is stabilizing. But again, like don't focus too much to what I just said, because like there are many equations inside, but the only key point message is that like we calculate the internal energy with VASP, and then we apply later script that can be this one or an improved one if you have, and you get the value of your energy included like the entropy. So this will be a good estimation for the G, and so it's the one that then you can put here. Okay?
Okay.
Good.
And because could you repeat that?
Yeah.
I mean there are 4 values.
Yeah.
And what are all of them mean?
It's written here. Usually in the command you always need to start to say what you do.
For
So the first one is give free energy of liquid. So in case you have your molecule in a liquid phase. The second one gives free energy of gas, in case you're in a gas phase. The third one is your internal energy. So it's simply the one without entropy. Okay, included the 0 point contribution, because this time you need to include it. And then the last value is just the entropy. Okay, so all these values are given in electron volt, I should have said before. And so what is happening is that here is the entropy multiplied by 10 to the power 3. So this value that you see here is are in milli-electron volt, okay?
Yeah.
Good?
Because you have changed the unit.
Because you change the unit, yes.
Okay. And the last part, because after the first president, after the first figure about the energy,
Yeah.
and the second part is about the Raman shift.
Yeah.
And what could I do with that?
I mean, as I said, like yesterday, what you get from that is the vibrational frequencies, okay? So for instance, I can make an example. Like if you go to, well, Raman, makes sense, and then you go with intermediate. So what I have here are a bunch of intermediate, okay? So let's take the easiest one. That is probably, okay, let's take the one that is not done. Okay, so let's take this one. So here, this system is basically OH adsorbed on copper. Okay, it's nothing different in this. And what you can do is that if you grab like the frequencies, yeah, because I need to go to frequencies. If you do a frequency calculation and you grab the frequencies, then you have all the vibrational frequencies of your molecules. Okay. So why this is important? Because experimentally with Raman or infrared spectroscopy, you try to identify these vibrational frequencies, and we can do the same with VASP. So we can help experimentally to assign some of the molecules that are adsorbed on the surface. Okay? So these things, so like for instance, this one is the OH binding, well, stretching, I think is defined. Okay? This first calculation, this first frequency. So this 3,671 centimeters to the power of -1. Okay, so that is important. That is one of the importance of doing frequency calculation, apart from helping you to calculate the Gibbs. Because again, here, if you want, you can calculate the Gibbs because you did this frequency calculation. Okay, and if you don't do frequency calculation, then you cannot calculate the Gibbs because there is no way you can get the entropy. Because in order to get the entropy, you need to have like a bunch of vibrational frequencies apart from any other. Okay?
I mean, that the Raman vibration is a precision of the frequency of any other.
Yeah, so the point is that usually in Raman, like, or at least what I understood as a DFT person, like what you try to do when you do spectroscopy is you try to get the vibrational like frequencies or like the fingerprints of the vibration of an intermediate on the surface. Okay, and in DFT we can do the same, but it's not that we calculate them. Like it's not that like, well, we can observe them experimentally because we are doing modeling, but we can calculate their vibrational frequencies. Okay.
Okay, I mean that the figure connected is the frequency.
Yeah, so the figure connected to the frequencies, and then I go back here. Yeah, it's because you see here that you have Raman shift centimeter to the power of -1, and you see that one of them is due to CO rotation and the other one is due to CO stretching with the copper. So if you calculate CO on copper with DFT, then you get exactly the same two frequencies. Okay? So that is the point, that here, like for instance, and I can make a very, very quick example because this paper is actually already out. Huh? Yeah, this is the experimental result, but you can see it here. So you see, like what was done experimentally was that they could see, or better say, because actually the better agreement is below. So experimentally, what they saw was that the intensity of one peak versus the intensity of the second peak follow this increase in the saturation of CO in the electrolyte. And with DFT, you can increase the CO coverage, and then you see that you have the same shift. So you cannot have a quantitative agreement, but you can have a qualitative agreement. Okay, so this panel is from DFT. This panel are experimental values. So what you can do with DFT is just to try to reproduce like experimental evidence. So in this case, you see like one of the peak is going up, the other one is going down, and that's why. And so experimentally, they could get this kind of intensity ratio, and we could reproduce the same. So vibrational frequencies in general, you do them because you can go to reproduce some experimental data on Raman or any kind of spectroscopy. Okay. More point. We have still 15 minutes.
For me? Okay, apart from the points that the Sishen has pointed, I have just a few questions. First of all, if you can put the class slides of yesterday.
Okay, yes.
It's just a small thing, but I want to know when it talks about when it talks about computing the simulations.
Then? No.
I think that's here. Yes. Before submitting, it uses a command which is sit or set.
Set, yeah.
Yes, I as I understand is that this is for including in the sorry.
Yeah, here. I think it's this set that you say, yeah.
Yes, this one. It's for including that line in the file, in the run file. But the idea is that we have to do every time we run a simulation before doing the.
No, in the sense that usually this VASP standard. This executor of VASP is much better than the standard VASP. But the problem is that we are doing this test on the C4, and the C4 can just use the version of VASP 5.3.5, and the version of VASP cannot use this executable. So for your standard PhD here, or like visiting period, like VASP STD is much better. So that's why like I'm not telling you to change this on your engine, because then you will need to change it back later. So I prefer you can change it, but then you need to change it later, because the standard one that you need to use is VASP STD. But since that failed on this version of VASP, then you need to change it. And so in this case, for the Anson, yes, you will always have to change it. So always is VASP
for the
STD.
We also have to change it, but when we will perform our own calculations, it's a line that it's not needed because as I understand, okay.
Yeah, because
you are using another version.
Exactly. So like what you will do when you submit, you will use. Okay, now I need to.
Yes, I don't know.
Yeah, you will not like. Oh, come on. Why am I annotating? No, I am annotated, but in white. So like what you will use here will be you would use 12 because you will use the C12.
Okay.
You can also use the C24, and you can also use more processors, but to me, the 1212 was already good because if you don't have crazy system is enough, and then you will use the version 5.4.4. Okay.
5.4.
And if you use this, then there is no problem. Then you use the VASP STD. Okay.
So we don't need to
exactly. So like in the future, this line is not needed. Okay.
Okay. And the other questions that I was preparing for today are more about the Inca, because there are a lot of commands that sometimes appear. For example, when we are starting to use Nmax and those kind of things and specify the cutoff, it just I think when we start with the water simulations. So I don't know which is the criteria to include more things on the Inca.
Yeah, so include more things in the criteria is because you increase the accuracy of your simulation.
Okay.
So the reason why you don't have them is because you basically are not asking VASP to do anything. Like this simulation that you did, that is probably one with the easiest Incar to line, is basically useless as a simulation, because what you take oxygen atom that is not a physical system, you optimize the electron structure. So you don't even do an optimization. So you don't even allow this atom to move. And in the case of the water molecule, so this one, well, you have more things because now you need to apply ab initio molecular dynamics. So usually this value is not that important because it's like, it's already like, I think it's already the default, it's normal, so it's not that important. The smear, we will see tomorrow, but as I said, it's just like the Gaussian smearing, etc. And max is the cutoff. And beware that, like in this case, they use Nmax, but then during the PhD, you will use Ncut because it's a more stable like parameters. But again, like nothing changes. Still, the cutoff energies, as we said yesterday. And then Ebrion. So now you have Ebrion because the default, I think, is Ebrion 1. So the default allows you to do an optimization, but here you want to do molecular dynamics. The molecular dynamics is a different system because the molecular dynamics is the one that allows you to check the dynamics of what is happening in your system. So usually what we do with your T, and that takes me a lot of time to understand, there is no time there. So you're just taking a configuration and you're optimizing it. So that means that you are optimizing the forces inside. So you take a snapshot, you say, you stop the time, and you optimize the force. Instead, the molecular dynamics let the time flow. So optimize the forces, changing the time. So that means that you see the time evolution of one of your systems. So you can see some.
So with Ebrion 0, you are doing a molecular dynamics simulation with time steps.
Exactly. With time steps. Here you define the steps. So you say that you want to do 100 steps. If you put 1000, it will be 1000 steps. And the pod team acts as the time step. So in this case, you are doing a molecular dynamics across 100 femtoseconds because you use 100 steps, and each of the steps lasts 1 femtosecond.
And NSW is about time steps. It's about molecular dynamics.
Yeah. So this NSW is the one that if you do optimization, so the one that we did for the oxygen before, account for the number of ionic steps. So if you want to play, you can try to add NSW equal to 100 in the oxygen.
But if we are including an Ebrion 0, this would be referred to the time steps.
Exactly. So this is in general either ionic steps or the molecular dynamic steps, depending on the ionic step, as you say. And then the other parameter, they are basically like the thermostat, the nose-over thermostat, and this is like a kind of formalism that you use like in molecular dynamics, well, for one of the ensembles. So like about that, I think we will go through that probably next week because I wanted to say yesterday, but I mean, there was too much theory, so we'll go through that like next week when they're discussing about that. But there are different thermostats depending on what you can change in the system. So like in DFT, since we have a periodic system, we always have to keep constant the number of particles in the system. We are also assuming that there is not transfer of heat with the surrounding thing, because actually there is not a surrounding. And then I think you also keep the overall energy constant as well, because that is always constant. So that's just a formalism, but we will see tomorrow. And the important point is that is the temperature, because since you are doing an ab initio molecular dynamics, and in, let's say, what you vary in this case is the temperature. So in this case, the initial one is 2000 Kelvin, and the final one is 2000 Kelvin. This is important because depending on this parameter, you can tune this parameter according to your experimental system. So usually, let's say another trick is that if you want to see a dynamic process that usually you don't see, then you may also increase it much more than what is expected to be. Like for instance, on the work that I did on copper oxide, I put a temperature of 700 Kelvin. There is no synthetic approach of copper oxide when they use 700 Kelvin. But we did it because then we could reduce the time step. Because at higher temperature, we can assume that the dynamic processes should act faster because the temperature is high. So like longer the incur, more precise your simulation will be.
I mean, the VASP always you reduce that at 0 Kelvin.
Yes.
And if we do this, then we have problem.
The point is that VASP usually do optimization at 0 Kelvin. So this, like all the other calculations you did, these are structural optimization. Okay. So all of them are 0 Kelvin. This is a different, it is still a VASP simulation, but it's a different simulation. Okay, this is ab initio molecular dynamics. That is a different class, let's say. And in this different class, the temperature should be different than 0. Because if you, I mean, at 0 Kelvin, you don't have dynamic process. Like at 0 Kelvin, everything is dead. Okay, so that's why you need to put a temperature. But in the other case, you cannot put a temperature because you are just optimizing the electronic configuration. It is much easier to optimize the electronic configuration at 0 Kelvin rather than at 2000 Kelvin. Yeah. And that's the reason why, for instance, when you're doing ab initio molecular dynamics like this one, before you optimize your system, so you optimize your system, you get a very well optimized electronic configuration, and then you apply on top of that molecular dynamics. Okay, you don't just take a structure, random structure, and you start ab initio molecular dynamics, because otherwise it will fail. Because before you have to have everything converged, and then you can study the dynamic processes on that.
And this means
number of time steps. The number of as mass. Yeah, this is telling you that you're using the node over thermostat.
Yes.
Okay. So like if you, and this is just, if you want, we can just I think I have it here. So if you go to mass -3,
it's to include this utility, I think.
Yeah. Okay, you see, like you open this is telling you molecular dynamics. Oh, okay, but this doesn't, okay. I mean, it's very small, so I think it's better, but basically like, okay, let's go like this. Thermostat. We will go through that like, okay. Let's see if we can increase this. No, I need to stop annotating before I think. Yeah, we do this window. Okay. Okay, then I close this one. So what you do is just, come on, why now it does not work? Well, we will go through that like next week when we do the ab initio molecular dynamics. But it's simply like based on the formula that you are using. Okay, so like you use this nose over thermostat because you're applying this calculation on top of your Hamiltonian. So you are solving Schrödinger equation, but as you see here, on top of what we have, you also add these two parameters, and these two parameters are basically like two corrections to include variation of temperature, and also like a fictional parameter that gives you a dependence on the heat, because the problem is that you're assuming that the heat doesn't change. And the point is that if you add, I mean, this is like standard like Boltzmann equation in general, that like whenever you add, like you increase the temperature, then also like the speed of your molecules get faster. So that's how you can play with the dynamics of your system.
Okay, and my last question would be, if you could you do LS, please? Because I don't remember the name of the. No, okay, but with the output files.
Yeah, with the output file. Yeah, sure.
With yes, for example, this. Yes, if you can build a VASP run point XML.
Okay, but yeah. So the point is that of course now it doesn't work because I am connected to my, like, I'm not building the two tunnel, so I'm not mounting the Teclafon folder on my computer. But if now I do like this, now I have mounted them. So now I need to go out, because in this case I was on my computer app, okay? Here instead I am in this computer, but I mounted Teclafon.
Okay.
So now if I do the same, I can use Python for VASP. So now I copy this, and now I do the same.
Okay. Okay, so I just go to I don't know, to see the key points. I think that's on electronic.
Yes.
View key points. And what I don't understand there, it's first I understand that those blue points are nothing.
And, I mean, these are just the periodic key points, because remember that you have a periodicity. This is the Brillouin zone.
Yes.
Okay, and this is your key point. You have one key point.
Yes, but you described it there at 0.0.0. Why it's in the middle? should be, I think, on a corner.
Yeah. You're right about that. Let's just check one thing. So, because it may be, I mean, I don't know if we put it like in Cartesian or in which chord.
I think it was Cartesian, but I don't know.
No, reciprocal. Okay, in unit of the reciprocal lattice vectors. Okay. Now then in principle you're right. I mean, this should be, yeah. So the point is that this Brillouin zone, I think that is centered in 0, 0, 0. You know, like I don't think that is like the standard cell that is centered in, like that as the origin. Like, you know, like you need to see it as a cell and not as the three vector. You know, so x, y, z, the center will be in 0.
But this is described somewhere, or
no?
Or it's just the...
No, probably not. Okay. But I mean, so yeah, like the problem is that in VASP, a lot of things are not properly described in the sense that, like, this you don't really see.
You cannot center it where you want.
No. I mean, I guess yes. Like probably if you change, you can try to change it to 1, 1, 1 here, then to run the same simulation and see if it's still there or not. I guess should be in another place. You know?
Yes, I understand.
You can try. That makes sense.
And it's about the key points. And what does what's the difference between the gamma? How you can put the gamma, and in this case, how put the rate. I mean the rate.
But I think we also put the gamma. No, here weren't there a gamma on top? Was not? Yeah.
I mean the rate.
Yeah, but you see that it's gamma point only.
Yeah,
okay. But I mean this line, yeah, like the point is that 0, 0, 0 in the reciprocal space is the gamma point. So the first line is just telling you what to do later. So the first line is just telling you that there, like you're just taking the gamma point. Yeah. And then the gamma point is the 0, 0, 0.
I mean the third line
yes.
is a rate, but the rate means what does it mean here?
Means that you are talking about reciprocal space. So means that, so what you're telling here is that you have just one key point, and that you will give the coordinates of these key points in units of the reciprocal lattice vector. Okay, so you can put this either rect or cart, depending on if you are talking about reciprocal active vectors or Cartesian. The reason why you have rect is because since the key points are in the space of the Brillouin, well, on the reciprocal space, doesn't make that much sense about talking about Cartesian, because then you need to convert it. Okay? But the only important point is that the gamma point is the center of the Brillouin zone. So the reason why they tell you gamma point only is because you just have a single point that is the gamma point, because it's in the center.
Okay, so if we wanted to put maybe 2 points, one would be gamma point and the other, I don't know, in a corner, for example, of that space. The idea would be, if we are using rec, it's like we are using, I don't know how to explain it. If we put 1 in one of the coordinates, we are making all the length of the vector.
Yeah, exactly.
Okay, so it's not Cartesian. In Cartesian coordinates would be maybe 12, for example.
Exactly.
But with 1, we are covering 12.
Exactly.
Okay.
So like if you do like that, I guess you will have 1 in the center and 1 somewhere else. Okay. The problem is that if you modify it, then you need to run again a simulation, because if now I save this,
yes.
then it doesn't change the VASP run, because on the VASP run you just have the key point that you use for your simulation. But if you save it like that and then you submit, then you can see. Yeah, it's something interesting for tomorrow indeed.
Okay.
So, well, we are already past 3 minutes, so if
for me it's
good.
It's all, yes.
I have one question about the podcast. Podcast is the unique input that we don't have to modify. The only thing we have to do is just to copy paste. And I saw that inside it we have like an infinite list of numbers.
Yes.
And I defined both the pseudo potential approximation and the exchange correlation.
Okay, now And I just I think that the best.
I would like to understand more the format of this.
I mean,
structure of the podcast, because since we never touch it.
Okay. So like as far as I, just to clarify a bit the things, because so now you have the pod car because it's done, but you know, for your own system, then you may not have all the pod car you need. So on Tekla Home, like usually we take on the Tekla Home of Nuria, you have a list of all the pseudo potential. But this is all Nuria. Okay, and I think it is one. Yes. So here you see that you have like a list of things, and you have also different pseudo potential depending on the functional. So LDA, PBE, PW91, PW91 USPP. Okay.
Okay, so the both are mainly related to the kind of exchange correlation.
Exactly. So like, so the point is that the pseudo potential, like the podcast give you the pseudo potential. Okay.
Yes,
So that, okay. And the point is that you have like the different exchange factors are given because you have different pseudo potential for the different functionals. So every functional estimate the exchange correlation things in a different way.
Okay.
So if you use, so there are two ways, like you can use different pseudo potential for a different functional, and you will have a different contribution of the exchange. Or the other thing that also work is that, and probably let's see if Pablo has something, because Pablo always work with very exotic system. Okay, probably this one. Or you can also include the things directly in the Inca. So there is also a way. Well, yeah, you see that these are very, very exotic systems. So you see that it's much, much, much more complex than what it is. So for instance, like it doesn't use GGA, it doesn't use like PBE, because they need much like more complexity. And then I don't see, no, probably here is not doing that. Let's see it, and Francis has it. Because the point is that there is also a way to include completely to include by scratch before, like how much exchange you want to consider in your calculation. Or maybe the easiest approach would be to go directly on internet and to go to hybrid functional VASP. Let's see. Okay, yeah. So this HCE03, this is one of the hybrid functional that allow you to include some of the exchange contribution specifically. So for instance, if you see this parameter, yeah, specify the fraction of exact exchange in the Hartree-Fock hybrid functional type calculation. So let's say like the exchange in general, like the approximation of the exchange comes from the pseudo potential, but if you want to have the exact exchange, so I guess derived, I don't know how, then you can do that using this hybrid functional, where you see here that, for instance, like you are using 0.25 of exact exchange. And if you use 0.50, then your accuracy is much better. But then the problem is that there is also taking much more time. So yeah, you see that the further shows, okay. The further shows so that the hybrid is selected for PB pseudo potential. So PB pseudo potential allow you to calculate the exchange, to approximate the exchange. But if you're not happy with that and you want to have the exact value, then you can include it with this parameter. Okay. So you are not approximating anymore the exchange correlation factor by like a special function of electronic density plus gradient of electronic density, but you are just calculating exactly how much this exchange should be for your system.
Okay.
But that takes a lot of time. So I was saying yesterday, like the difference like between half an hour and 30 days.
Okay.
So that's the reason why you never use these things, these like exact exchange, unless you don't really have some specific band gap calculation or electronic calculation and need to be very precise. Okay. Yeah.
The last question is always related to this, the pseudo potential approximation. since we say that we use this approximation for the inner shell electrons, does it mean that in our final system with this, namely the set of constant equations, we reduce the number of equations with the pseudo potential, right? Or,
yes. Yeah, because you're accounting for less electrons.
Okay, then we are.
Yeah, so that's the reason why you use pseudo potential.
Okay.
Because you don't want to. Like there are two different things. Like because the podcast is not just pseudo potential. There are also other parameters there. So the pseudo potential are to reduce the number of electrons. Okay.
And to reduce the number of equations.
Exactly, the number of equations. And then on another level, there is, for the functional, the contribution of the exchange correlation part. Okay? That also speed up your calculation because you're approximating it and you're not calculating it exactly. Okay?
And this factor will never use.
No, not in your, for sure, not in your system.
And Amex maybe.
Amex. So like Emax, okay, but
Amex.
Like
this?
Like that. Okay, I never heard that.
No, never.
Okay, Amex. Okay, but I mean, again, we will go through the magnetism, I think, 3rd or 4th lectures, but the magnetism, you can use it if your system is magnetic, and you play with that, but you just play with that to increase the speed of electronic optimization.
I mean, just the Amex, without mag.
Yeah, but I mean, it's very similar. Like mag is with the magnetic, let's say, and then if you remove mag, is a same mixing parameter that is about like how the formality of the FT is built. But let's say it's just optimizing your electronic structure with a different how do you call it? Like with a different approach, so that your calculation can be faster or slower. I mean, it's not changing your final result. It's just about getting your result faster or slower. So you just change it in case your result doesn't work or takes like ages to converge. Okay? Good? Yes. Okay, then I think that for today we are done. I mean, we're already 10 minutes late. We meet tomorrow at 10, and tomorrow we'll also define much better all these things that I said about like VASP. Okay? Okay, good. And also give you, well, tomorrow we'll also present and also update in the group the updated timetable with the lectures that we need to see, so you can organize and we change in case somebody has conflict. Okay? No, now you don't. Now you have all the podcast that you need directly on the answer. So now you don't need to worry about how to generate further podcast. That is something that we do at the end. Okay? Because it's very easy. I mean, also there is. So for instance, in my case, I have a script, and that's again to tell you why it's so important to have script. No, but actually, like for instance, in my case, I have a script that is spot. That what it does is simply take the element directly from the postcard and generate the postcard already. Okay. So that's the reason why I want you to do some script, because you will see that actually like 80% of like a PhD in DFT is about scripting. It's not about doing simulation. Because at the end you get to have, I mean, the simulation at the end is the computer result, but you need to find a quick way to simulate all your system. Because as I was saying, now it's okay because we have 10 simulations to run. But at one point you may have 1,000 simulations to run. So you cannot enter each of the systems. Okay, now I generate this podcast, now I generate the other podcast, now I generate the other podcast. Because otherwise you will spend 1 month to do something that you can do like in 3 minutes. Well, maybe 5. Okay? Good. So I think that it's okay for now. So I just close everything. Thanks, Mariam, for listening. And then, yeah. See,
thank you very much.
Yeah. Do you have any point or question? I didn't ask.
No, actually.
I
should do it by myself. Yeah, it's a little hard to understand this way.
Yeah. No, I know. No, and mostly like that. Yeah, before you should try yourself, and it will be a bit easier to follow, But don't worry about it. Just let me know if you need anything more from these.
Sure.
Okay.
Sure. Thank you very much.
Good. Bye.
Have a nice day, all. Bye.
Bye.